Welcome to G Fun Facts Online. Today, we are traveling to the frozen, silent reaches of our solar system, far beyond the orbit of Neptune, to investigate a mystery that has haunted astronomers for nearly a decade. It is a story about gravity, invisible ghosts, and a radical idea that suggests our solar system might be home to something far stranger than a planet. We are talking about the possibility that Planet 9 is not a planet at all, but a primordial black hole from the dawn of time. To understand why serious scientists at institutions like Harvard, Caltech, and Durham are considering a black hole in our backyard, we first need to understand the anomaly that demanded its existence. This story doesn't begin with a telescope image, but with a mathematical puzzle. The outer solar system is populated by trans-Neptunian objects, or TNOs. These are the icy debris left over from the formation of the planets, drifting in the dark. For the most part, objects out there, like Pluto, follow predictable paths. But as astronomers began discovering more distant objects, a peculiar and unsettling pattern emerged. A specific group of these icy bodies, known as extreme TNOs, including objects like Sedna, 2012 VP113, and Lelea Kohonua, are not moving randomly. They share strangely clustered orbits. Their points of closest approach to the Sun occur in the same quadrant of the solar system, and their orbital planes are tilted at similar angles. If these objects were randomly distributed, the odds of such a clustering occurring by chance would be approximately 1 in 500. It looks suspicious, as if a conductor were guiding an invisible orchestra, herding these icy bodies into line. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown published a landmark paper proposing a culprit. They calculated that a massive perturber, a ninth planet roughly 10 times the mass of Earth, must be orbiting on a highly eccentric path, some 400 to 800 astronomical units from the Sun. For context, Pluto averages about 39 astronomical units. This hypothetical Planet 9 explained everything. It explained the clustering, the high inclination of certain objects, and even the subtle tilt of the Sun's axis relative to the planets. The hypothesis was elegant, and the race was on to find it. Astronomers assumed Planet 9 was a super-Earth, or mini-Neptune, a class of planet common in the galaxy but missing from our own solar system. Teams around the world scoured archival data from the WISE mission and the Subaru telescope. They reasoned that a planet of that mass, even cold and distant, should emit a faint heat signature, leftover energy from its formation slowly leaking out as infrared radiation. But years passed. Surveys covered the most likely orbital paths. Nothing was found. The constraints tightened. If Planet 9 existed, it had to be colder or smaller than standard models predicted. Or perhaps it was hiding in the busy background of the Milky Way's galactic plane. The silence from the data was deafening. Then, in late 2019, a radical hypothesis emerged from the halls of theoretical physics that turned the search on its head. Physicists Jakob Schultz and James Unwin asked a provocative question. What if we haven't found Planet 9 because it isn't a planet? What if the object shaping our solar system is a relic from the Big Bang? They proposed that Planet 9 could be a primordial black hole. Now, when we think of black holes, we typically imagine stellar mass black holes, the corpses of massive stars that collapsed under their own gravity. These are huge, minimum 3 to 5 times the mass of the Sun. But in the 1970s, Stephen Hawking and Bernard Carr theorized a different kind of black hole. In the first fraction of a second after the Big Bang, the universe was a hot, dense soup of energy. It was not perfectly uniform. Quantum fluctuations created tiny pockets of slightly higher density. If a pocket was dense enough, it could collapse directly into a black hole before a star ever formed. These are primordial black holes, or PBHs. Unlike stellar black holes, PBHs can come in any size. They could be as small as a proton or as massive as a galaxy. However, Hawking radiation, the quantum process by which black holes slowly evaporate, imposes a limit. PBHs smaller than a mountain would have evaporated by now, ending their lives in a flash of gamma rays. But those heavier than a large asteroid would still be here today, lurking silently in the cosmos. Schultz and Unwin looked at the mass required to explain the Planet 9 anomalies, which is 5 to 10 Earth masses. This sits comfortably within a window of allowed PBH masses that haven't been ruled out by other observations. But here is the mind-bending part. If you were to take 5 Earth masses of matter and crush it into a black hole, the resulting event horizon would be shocking. It would have a diameter of roughly 9 centimeters. That is the size of a grapefruit or a bowling ball. This tiny size explains why we haven't seen it. A 9-centimeter sphere at 500 astronomical units reflects zero sunlight. It has no surface to heat up. It is the ultimate stealth object. Yet gravitationally, it acts exactly like a 5 Earth-mass planet. To a distant object like Sedna, gravity is gravity. It doesn't care if the source is a rocky world or a singularity. This theory also solves another problem with the planetary hypothesis, which is the capture problem. How does a solar system acquire a massive super-Earth at such a wide orbit? It couldn't have formed there because there wasn't enough material. It must have been ejected from the inner solar system, or captured from a passing star. Both scenarios are statistically unlikely. However, Schultz and Unwin calculated the probability of the Sun capturing a rogue free-floating planet versus capturing a PBH. Surprisingly, the odds were comparable. If the galaxy is teeming with PBHs, which is a potential explanation for dark matter, then the solar system capturing one of them is a plausible event in its 4.6 billion-year history. So, if the object is a black hole, conventional telescopes are useless. We cannot see it. But that doesn't mean it is undetectable. In 2020, following the excitement of this hypothesis, Harvard astronomers Amir Siraj and Avi Loeb proposed a method to catch the invisible intruder using accretion flares. Planet 9 resides in the Oort cloud, a vast spherical shell of icy comets surrounding our solar system. While space is empty, it is not perfectly empty. The Oort cloud is populated by trillions of small, icy bodies. Siraj and Loeb calculated that a 5 Earth-mass black hole would occasionally plow through this debris field. It wouldn't need to hit a large comet directly. The black hole's gravity would capture small icy rocks, dust, and gas from the interstellar medium. As this material falls toward the event horizon, it accelerates to near light speed, heats up due to friction, and emits a sudden, bright burst of radiation. This is a flare. This is where the next generation of astronomy comes in. The Vera C. Rubin Observatory, currently nearing completion in Chile, will conduct the legacy survey of space and time. It is essentially a movie camera for the universe, scanning the entire southern sky every few nights. According to Siraj and Loeb's calculations, the PBH should encounter enough material to produce a detectable flare a few times per year. These flares would last for days or weeks. Because the Rubin Observatory scans the sky so frequently, it is the perfect instrument to catch these transient flashes. If Rubin starts detecting unexplainable sparks in the outer solar system that move along a consistent orbital track, we may have our smoking gun. A planet wouldn't flare, but a black hole would. Now, you might ask, why not look for the black hole's own glow? As mentioned, black holes emit Hawking radiation. The smaller they are, the hotter and brighter they are. However, a planetary mass PBH poses a frustrating paradox. It is too heavy to be bright, and too light to be active. A 5 Earth mass black hole has a Hawking temperature of near absolute zero. It emits less radiation than the cosmic microwave background. It is effectively frozen and dark. On the other hand, it is not massive enough to have a stable, bright accretion disk, like the supermassive black holes in galactic centers. It only flares when it eats. Thus, we must rely on the environment rather than the object's intrinsic emissions. There are even more ambitious proposals to find it. In May 2020, theoretical physicist Edward Witten, a titan of string theory, proposed a direct approach. If we can't see the black hole, we must feel it. Witten suggested using technology similar to the Breakthrough Starshot initiative. The idea is to launch a swarm of hundreds or thousands of miniature spacecraft, weighing only grams each, accelerated to 1% of the speed of light using powerful ground-based lasers. You don't need to hit the black hole, which is tiny. You just need to fly near it. The fleet would be launched toward the general sector, where the TNOs suggest Planet 9 is hiding. As the probes travel, they continuously broadcast simple ping signals back to Earth. If a probe passes within a certain distance of the PBH, the black hole's gravity will warp spacetime, causing a Shapiro delay, which is a measurable time delay in the signal reaching Earth. By analyzing the timing of the pulses from thousands of scattered probes, we could triangulate the location of the invisible mass. While we wait for futuristic probes, another method relies on the bending of light, known as gravitational microlensing. When a massive object passes in front of a distant background star, its gravity acts as a lens, magnifying the star's light for a brief period. The duration of this brightening depends on the mass of the lens. A star might cause a lensing event lasting weeks. A planet might cause one lasting hours or days. APBH would look exactly like a rogue planet in a microlensing event. The Optical Gravitational Lensing Experiment, or OGLE, has been monitoring millions of stars for years. In 2019, they released data showing an excess of short-duration microlensing events. These were interpreted as a population of free-floating rogue planets in the Milky Way. However, the PBH proponents argue that these events are consistent with Earth mass and super-Earth mass black holes. The distinction is difficult to make with ground-based telescopes because the atmosphere blurs the image. This is where the Nancy Grace Roman Space Telescope comes in. Launching around 2027, it will perform a high-cadence microlensing survey from space. Unlike ground telescopes that just see the brightness change, Roman is precise enough to see the background star's apparent position shift as the lens passes. This allows for a precise calculation of the lens mass. If Roman finds way more rogue planets than planetary formation models predict, it would strongly support the existence of a PBH population. As research continued into the mid-2020s, a new detection vector emerged closer to home. In late 2024, researchers from MIT and other institutions proposed that we don't need to look to the Kuiper Belt to find evidence of PBHs. We can look at Mars. If PBHs are the dark matter, they are not just sitting in the outer solar system, they are swarming through the galaxy. Statistically, asteroid mass PBHs should fly through the inner solar system fairly often, perhaps once per decade. Using decades of high-precision telemetry from Mars landers and orbiters like Viking, Pathfinder, and Perseverance, scientists can model the exact orbit of Mars to within centimeters. A PBH flyby would exert a tiny gravitational tug, causing a wobble in Mars' orbit that deviates from the predictions of standard physics. Recent papers from 2025 suggest that reanalyzing old data could reveal these ghost tugs. While a Planet 9-sized PBH is too rare to fly by Mars, the smaller asteroid mass cousins might be detectable this way. The implications of this hypothesis extend far beyond our solar system. A 2025 paper raised a disturbing question. Have we already discovered PBHs and misidentified them as planets? We detect most exoplanets indirectly, via the wobble of their star. A 5 Earth mass PBH orbiting a star would cause the exact same wobble as a 5 Earth mass super-Earth. If the object doesn't pass in front of the star, we have no way of knowing its radius. We just assume it's a planet. This suggests that our catalogs of super-Earths might be contaminated with primordial black holes. It forces a re-evaluation of exoplanet demographics. Are some of those habitable zone worlds actually singularities? Ultimately, the stakes of the Planet 9 PBH theory are astronomical. If Planet 9 is a black hole, it solves the longest-standing problem in cosmology, which is the identity of dark matter. For decades, the leading theory for dark matter has been weakly interacting massive particles, or WIMPs. But despite billions of dollars spent on detectors, not a single WIMP has been found. If the universe is filled with PBHs, they would behave exactly like cold dark matter. They have mass, they interact only via gravity, and they don't emit light. Finding a PBH in our solar system would be the Rosetta Stone. It would prove they exist, and imply that the 85% of the universe's mass we call dark matter is just ordinary matter, collapsed into holes during the Big Bang. It would mean we are not surrounded by exotic, ghostly particles, but by a sea of ancient, invisible stones. As we move toward the late 2020s, the Vera C. Rubin Observatory stands ready to open its eyes. If it catches a flare in the dark, or if the Roman telescope spots a lens with no light, our picture of the solar system will shatter. We will have to accept that we share our home not just with rocks and gas giants, but with a piece of the Big Bang itself, a tiny ancient monster prowling the frozen wastes beyond Pluto. Whether Planet 9 turns out to be an icy super-Earth or a grapefruit-sized singularity, the search itself pushes the boundaries of our technology and our imagination. But if it is a black hole, it will be the most profound discovery since the realization that the Earth is not the center of the universe. It will mean that the dark, empty spaces between the stars are not empty at all, but filled with the invisible remnants of creation.